Back, everybody. Let's go ahead and get started. Keeping track, this is day 21. Today I will, this will be my last of the Olefin Metathesis. And then Thursday of this week will be your Wikipedia page presentations. A few folks have asked about the format of those presentations. It's meant to be fairly informal. So what will happen is each member of the class will have 3 minutes to come up and essentially walk us through, scroll through your Wikipedia article. You don't need to prepare a separate PowerPoint. To save transition time on my computer or on one of the TA's computers, we'll have all of them loaded up. So you can come up and scroll through. If you're not able to attend in person, then you would just do a screen share of your page over Zoom, and we will do it in reverse alphabetical order by last name. So that those who are normally last in that format will go first. Does that make sense? Are there any questions on those presentations? And then there'll be, if we stick to 3 minutes per person, and then we have a minute of question slash transition time, then we should be just about good for it. And I'll bring something to snack on. Next week, Tuesday, we'll have another guest lecture from the folks at Merck representing the discovery process team. That will be one to look forward to. And then Thursday, we'll have the final exam, same format as the midterm, 2 hours, with the exam designed to be about an hour and a half. And then what other administrative matters are there? There's Camille.
Problems is due Thursday morning, and I have an office hour tomorrow at 11 or 2. No, I can't remember. Tomorrow at 2 in the 4th floor conference room.
Okay, and then as a reminder, on the fly, we made the adjustment to the syllabus to not cover the CH activation lecture. If you're interested in that, which some in the class might be, I would just direct you to the recording of the class, which is on YouTube from last year. You won't directly be responsible for that material on the final, but if you're curious to learn and if it helps you to rehearse concepts that you're really responsible for, then please check that out. Maybe you could just share the link, Camille, to that lecture from last year in case folks want to check that out. I'd be happy to do that again, but I know that everybody is busy these 2 weeks, and adding more classes is not the way to solve everybody's busyness. Okay, so we'll wrap up. We have about a page of notes on C heteroatom bond formation as it pertains to cross-coupling, and then the bulk of the class will focus on olefin metathesis. Some of the heteroatom bond formation material we got some exposure to during the guest lectures, particularly BMS. The folks from BMS had a nice discussion of some of this. So it might be review, but it's still good to go through formally. Okay, so let's start off by taking a look at a historical overview of this suite of transformations we now refer to as Buchwald-Hartwig type amination, and what the key precedents that their contributions built upon. As early as the 1980s, this potential power and utility of C heteroatom bond formation at palladium along a palladium 0-2 redox couple was appreciated, and there's important contributions by the lab of Victoria Megiddo, and you'll of course recognize this name from contribution to Megiddo Stille reaction. This can be thought of essentially as an amino. The key point here is that the transmetallating partner is a tin amide. So rather than transmetallating and transferring a carbogenic group, it's transmetallating and transferring an amino group. The reaction works relatively efficiently. You see no real special tricks in terms of catalyst design other than the use of the orthotoluol, tris orthotoluol phosphine ligand, which is bulky compared to triphenylphosphine and helps with the challenging C-heteroatom reductive elimination step. But of course, this transformation is not widely used today because these tin amides are not super convenient coupling partners. I think the only one that is readily available, commercially available, is the one shown. So for any variant on that, you would need to independently prepare it. We'll talk about that in a moment. Roughly the same time, just 1 year later, there was an important contribution from our colleague Dale Boger, who came to study carbon-nitrogen bond reductive elimination from palladium 2 centers in the context of a natural product synthesis campaign. So here now, in a stoichiometric sense, with respect to palladium, the Boger group treated this ortho-bromohaloaniline component with palladium 0. What do we get here, Shenghua?
Carboxyl.
We get what? Sorry.
The corresponding carboxyl.
Okay, what's the first step?
Oxidation.
Oxidative addition. Okay, so we're getting palladium 2. Nitrogen bound, so this was chelation stabilized, and then I think Shenghua helped us with the next step. He said the final product in the end will be the corresponding carbon. And if you look at this in a stoichiometric sense, this is really the whole shebang. We don't need tin amide in this case. The oxidative addition step, of course, is well precedented from the prior work in palladium-mediated cross-coupling. And the key point here is this CN reductive elimination from a palladium 2 center, which will be one of the key constituent elementary steps from in the contamination. So this is a very important contribution in the Boger group that shouldn't be underestimated.
Gary, what are the properties of those tin amides? Like, are they particularly nucleophilic, or are they kind of dead?
Are they particularly nucleophilic?
Or like, are they water? Are they stable to air?
Well, I think they're less like if you're thinking about corresponding lithium, magnesium amides, they're less nucleophilic there. So there's probably an analogy to be made here between a classical Kumada and classical Stili to, let's say, a reaction of a magnesium or lithium amide versus the corresponding tin amides, the Isa Stili. So they're not, they have tempered nucleophilicity. I think the functional group compatibility is reasonable. So the turning point in this area of research, which for a historical perspective, I direct you to this nice review from the Israeli Journal of Chemistry from just a few years ago, were parallel studies performed contemporaneously by the Hartwig and Buchwald group. And you see in just a few years, this went from sort of a curiosity to something that started to have the foundations of a workhorse transformation. So Hartwig group came at this from a mechanistic perspective, revisiting the prior work by the Megiddo group and focusing specifically on this key reductive elimination step. So in this study by Hartwig from 1994, they were able to isolate several of the key proposed intermediates and then demonstrate unambiguously reductive elimination from the palladium-2 center. Buchwald group came at this more from a synthetic perspective, and this ties into a little bit of Alex's question. So as I mentioned, a disadvantage with the tin amides is that there aren't many that are commercially available. But the Buchwald group, being very practically minded, came up with a nice solution. They found that whatever coupling partner that you wanted to incorporate into your final product, you could mix that together with essentially the lone commercially available tin amide, allow them to equilibrate and then purge with argon, and take advantage of the fact that dimethylamine here is volatile, and under these conditions, 80 degrees with an argon purge will just be liberated from the reaction mixture. And then under based on Le Chatelier's principle, you can drive the equilibrium to formation of the desired new tin amide, which then you can use in situ in subsequent CN coupling. So a very practical solution to this issue of the fact that there aren't many tin amides that are commercial. But of course, nobody, well, maybe I shouldn't say nobody. Few people these days use this tin amide protocol. So what was the key advance that came in the next year? The discovery that tin could be avoided altogether through the use of strong, sterically bulky bases. Again, papers in quick succession from Buchwald and Hartwig. I think Steve came to give a lecture for the Riebeck-Sessler Symposium recently and talked about some of the history and reception of this work at its time of publication. I won't rehash that here, but that was interesting to hear. So you see in the Buchwald report now, N-methylaniline is competent coupling partner in combination with sodium T-butoxide. The Hartwig publication, 1995 publication, uses prolidine in combination with lithium HMDS. Why is the strong sterically bulky base important? Well, we heard a little bit about this from during the BMS lecture. It has to do with this concept of soft deprotonation. Okay, let's take a look at the catalytic cycle here. I'd like to draw everyone's attention to this important mechanistic study that includes as one of the co-authors our colleague Donna Blackman. I think Donna likes to say that this is an interesting paper where it was she was an author in combination with Buchwald and Hartwig, and I think she's listed somewhere in the middle. So she likes to say that she kept them at arm's length during the discussion. But this is a study that resolved several mechanistic discrepancies up until this point. The now accepted catalytic cycle looks something like this. Again, this was, I think, almost verbatim on a BMS, on one of the slides from BMS, so we'll go through it quickly. I'll ask for someone to help me with this. Start with a palladium pre-catalyst. This could be palladium 0 plus ligand. It could be palladium 2 with the ligand already installed. We get to the active palladium 0 species that's on cycle, oxidative addition, first to give the trans adduct, which will eventually isomerize to the cis form. And then, let's see, okay, let's walk me through this step. Elin, what's going to happen here?
We'll replace one of the ligand.
Okay, which ligand? Bromide, okay. Why do you think bromide?
Either the bromide or just like from the ligand, because I remember the amine will coordinate as the L-type ligand first.
Okay.
And base will come and it will become a X-type.
Okay, perfect. So let's, I think that you got it there. So let's, so in that case, if you're telling me that it's going to coordinate as the L-type ligand, then if it displaces an X-type ligand, it will form a cationic species, which can happen, but let's say, we generally try to avoid that. So you're saying to form this adduct amine displaces L-type ligand. Now we're primed for this soft deprotonation. So this is essentially the difference between the azactyl and now the Buchwald heartbreak, is that rather than a transmetallation, we have ligand exchange followed by soft deprotonation. And then there are several things that could potentially go wrong here. So I have a few off-cycle species. So help walk me through what could potentially go wrong here. What are some concerns you would have if you had never encountered this reaction before and someone proposed it?
Off-cycle species. To me, from the intermediate that's shown.
Yeah, that's right.
Which intermediate?
From this intermediate, these off-cycle potential off-cycle species.
So I would guess there is a potential that's the NP reductive elimination can happen, but it's not that easy.
Okay, that's one thing to be concerned about.
Do beta hydride elimination.
Aha, okay. It would depend what your R and R2 groups are, of course, but let's draw out one of them just in a more suggestive way. This. Got it here. Beta hydride eliminate, and we saw this actually is a way in which we sometimes reduce palladium. In this case, we would have needed to, I guess, use a ligand. This is a way in which we can reduce palladium 2 to palladium 0 to get on cycle. This beta hydride elimination. Here, this is going to be deleterious. And if you start to see evidence of imine formation or corresponding aldehyde formation from hydrolysis, this is problematic. So beta hydride elimination is one. And that's very likely to be irreversible. And then what's another?
So some mutant replace another ligand.
Beautiful. So there's nothing here in principle that is stopping you from coordinating another equivalent of amine. Here. And this also would be one is L type, so that we can get there from this particular feature. But it can also be both coordinating L type. Good. Any questions on that? Okay, let's take a look then at problem of the day number 3 from last time. If you don't have that worksheet handy. Worksheet. So let's take a look at this key productive CN reductive elimination step. I'll just read this. There's reductive elimination to form C and PN bonds occurs more rapidly from complexes bearing basic amido groups, as shown below. So more basic, faster reaction. Those are plausible explanations, plural, ideally more than one, so that the next question makes sense. And then propose an experiment to distinguish among these. So take a minute to think about that on your own, then a minute to discuss with your neighbor, and then we'll discuss as a class. Okay, let's discuss some possibilities here. More basic, faster rate. So the series dialkyl is faster than alkyl aryl is faster than dier. Just focusing on the CN reductive elimination step. So what are some possible hypotheses that we can jot down here?
Like more nuclear delivery, more likely to be the secondary coordination.
Well, it's already coordinated, so we're just focusing on the reductive elimination step. But I think your idea is on point here, which is, if I understand correctly, essentially a more nucleophilic lone pair. That is true, right? That hypothesis makes sense. More basic intrinsically means a higher lone pair electrons that are higher energy orbital, i.e. more nucleophilic.
Hard to say that because if it's a more nucleophilic or basic amine, then it's going to be like a stronger sigma donor, and like therefore make the palladium more electron rich, but for reductive elimination.
This is a good question, and there's a lot to unpack here, Anthony. This is a very astute series of observations. So the question here is about the polarity of this palladium here. So as we have a more electron rich versus more electron poor substituents on R1 and R2, we're changing the how this bond is polarized. We would say when R1 and R2 are aryl, the overall amido substituent is more electron withdrawing. And And the overall effect is that this bond becomes stronger. So a more polar bond in this case is a stronger bond. And that would lead to ground state stabilization. So if we're thinking about the two factors we need to consider, it's just one elementary step, right? It's where the ground state sits and then where the transition state sits. So as we have more polar palladium nitrogen bond, stronger bond, and it's going to sit at a lower ground state energy. Now, you also made an argument that there's some subtlety to it, which is as the metal becomes more electron rich or electron poor, we need to consider the effect that that has on reclamation. But in this case, it's convoluted by the fact that one of the group that is having that electronic effect on the metal is the one that's involved in reductive elimination. So if we have a ligand, an ancillary ligand L, let's say the L groups, we're making them a more electron poor, then we'd say for sure that's going to accelerate reclamation. When it's one of the groups involved in the bond forming step, there's some subtlety here. It depends whether it's acting as effectively the nucleophile or acting effectively as the electron. Does that make sense? In this case, it's acting effectively as the nucleophile. I think this is a common thing. Even you'll see this in the literature, people confusing this phenomenon where you have to take special care on electronic trends when one of the electronic trends are with respect to a group involved in bond formation. Yeah. And does anybody have anything different? So the first is more of a transition state, stabilization, destabilization argument, and the second is more of a ground state. Stabilization, destabilization argument. Any other thoughts here? And then how would you potentially disambiguate between these two possibilities?
Actually put on ligands, like for the more polar one, you could put on ligands that also change the polarity of the shell species. See if that has like any bearing.
That's true, but that might also, yeah. So you're saying change the electronic properties of L and see how that varies. Great, but I think you could maybe make an argument that either of these overall hypotheses could be explained by whatever trend you observe there. Any other thoughts on this? Making this distinguishing between these pathways directly is challenging because any change you make to R1 or R2 not only affects the nucleophilicity of the lone pair, but also affects the palladium nitrogen bond strength. So one of the ways that this has been approached is to look at the corresponding series of palladium alkyl complexes, where alkyl, for example, is the enolate type, where you don't have this convolution of lone pair effect and bond strength effect. You can just zero in on just the bond strength effect. And indeed, what they find in this series is that more polar palladium carbon bonds are, or maybe I should say, to make this more clear, I should say less. So these are arguing in the same direction. More nucleophilic lone pair, less polar palladium nitrogen bond. So you can look at the corresponding series, the carbon series, where the lone pair is not present, and you see that this term still holds, which if you reason by analogy, then allows you to conclude that this is at least a dominant effect in the palladium carbon nitrogen reductive elimination series as well. And this is summarized in this review from Harvard, if you're curious. Any questions on that? some of that quickly. Okay, likewise, there's been progress in carbon-oxygen bond formation, carbon-sulfur bond formation, and as you saw in Nick's lecture, carbon-fluorine bond formation from palladium to centers. There's a general trend here that the harder that reductive elimination is, the longer it took historically to develop the catalytic version of that reaction. So CC bond formation came first, then CN, then CO, and CF. That's the general difficulty of reductive elimination. As well, more and more tailored ligands, more and more finely tailored reaction conditions were necessary. You see in the case of the esterification, now we're getting bulkier ligands, tributylphosphine in the case of Cartwig, John Phos, which is a biaryl, dialkylphosphine ligand in the case of Buchwald. And the overall story here, the catalytic cycle is largely the same as what we've seen before, so I won't dig into the details here. A related reaction, which some in the audience may have run this, if you pursue a career in medchem, you almost certainly will run this reaction at some point. It's the Chan-Lamb coupling or Evans-Chan-Lamb coupling. This is a complementary reaction, complementary method for CN bond formation. At a very high level, a lot of the nitrogen coupling partners that work well for palladium don't work well for copper and vice versa. So there's complementary coverage here in terms of scope. In terms of catalysis here, there's a key difference, which is that in essence, you're coupling one nucleophilic component with a second nucleophilic component. And thus, to turn over, just like if you think about this in main group chemistry, if you have two nucleophiles, something needs to accept the electrons from their collision. You need a terminal oxidant to turn this over. And in this case, O2 is the most commonly used terminal oxidant, although not the only compatible terminal oxidant. In the interest of time, I won't go through the catalytic cycle here, but and to be frank, it's somewhat complex and has been the topic of some debate in the literature. But this is believed to involve a high valent copper-3 intermediate. So when you go to higher oxidation state, we saw in Nick's lecture, otherwise challenging reductive eliminations now become competent, and that's the case here. CN reductive elimination from copper-2, typically slow. CN reductive elimination from copper-3 is more facile. So O2 serves as the oxidant to get up to copper-2 to trigger this reductive. And then I just draw your attention to chemistry in which the logic of cross-coupling is essentially superimposed into three-component variants. And this is not textbook stuff by any means, but just I put it here for you to, in case it's helpful for you to reading the modern literature. I call these conjunctive cross-couplings, where they unite the typical components of a cross-coupling across a third reaction component. That third reaction component can be something like CO, SO2, carbene, it can be a pi bond, either an alkyne or an alkene or even an alene. So here's an example of that type of coupling from the lab of Laroc, a three-component conjunctive Suzuki type coupling across an alkyne. So here, when you see this type of coupling, you just think about the logical framework that we've established for palladium cross couplings, oxidation addition, transmetallation, reductive elimination, and then you're going to have some intervening steps with the conjunctive component. So in this case, coordination of the alkyne, migratory insertion, which will then precede transmetallation. And then here's an example from my group where we do essentially the same thing, a conjunctive cross coupling across an alkene that contains a directing group under nickel. Good. Any questions on that? Okay, let's call that a wrap then for cross coupling and CC and C heteroatom bond formation. Let's shift gears now and discuss olefin metathesis. Olefin metathesis really, what we'll cover here, I think goes hand in hand with some of the themes that came out of the carbene, the metal carbene, metal multiple bonded species lectures. And sometimes these metathesis is covered back to back with carbenes. That's a logical way to do it, but here we just cover it towards the end. But I want to get everybody reflecting on what we covered in the carbene lecture, where there's this question of polarization of the metal carbon double bond. There are cases where the canonical, the limiting scenarios are extreme Fischer and extreme Schrock character. Extreme Fischer, those are like metallocarbonyls. Extreme Schrock, remember we think of those as like double Grignards or double organolithiums in terms of polarization. And the catalysts, the metals that tend to work best for olefin metathesis have reactivity that is much more in the middle ground here. So if those are the two extremes, if one is the dark side of the force and one is the light side of the force, then metathesis catalysts are like the gray side of the Let's see what I mean by that here. So the key step in metathesis that we'll see again and again, you'll go to sleep dreaming about this intermediate, is the metallocyclobutane that is formed via 2+2, metallo 2+2 between a propagating metal carbene and a olefin. In productive metathesis, what needs to happen next is a retro 2+2. So the overall process is a changing of the partners. I think they call this like a molecular swing dance or something to that effect. But it's not the only thing that can happen. So what are some other side reactions that could potentially happen from this same intermediate? Some of these we've even seen before in class. What do you think, Jenny? Of what? You got it. So it's reductive elimination to make a cyclopropane, right? Then in that case, we have metal now that no longer contains a carbene. So you can see immediately how this would be a catalytic deactivation pathway. What else is possible? Any volunteers? Let me see if I can draw this suggestively. Aha, beautiful. So beta hydride elimination followed by CH reductive elimination. We'll get you maybe I'll draw this intermediate so that it's a little bit more clear what I mean by this. We'll get you to the corresponding alkene. And also the metal, reduced form of the metal, not catalytically active. And which of these processes is preferred depends not only on the ligand environment around the metal, but of course the metal itself. So one general trend is that as you move right to the periodic table, CC reductive elimination becomes more favorable from this type of intermediate. That's why you never have seen or heard of a rhodium-based olefin metathesis catalyst. That's too far right on the periodic table. Once you get this intermediate, bang, CC reductive elimination, and you're toast. And that has to do with the intrinsic electronegativities of the atoms or the metal elements involved, as well as other trends that we covered previously. Let's discuss now. What did I do here? Some synthetically important reaction types, and then we'll unpack some of the mechanistic details of these transformations. One class is called SHOP, shell higher olefin process. It's really like a form of cross metathesis that is specific to the petroleum refining and upgrading industry. It's a means by which shorter chain alkenes can be converted into longer chain alkenes, which as we have seen, ultimately then get converted through isomerization and hydroformylation to things like linear alcohols that are useful in detergents. So this is a workhorse reaction for making more higher carbon count alkenes, but it's not something. It typically involves heterogeneous catalysts, high temperature, not something that you will encounter much in your career as an organic chemist. Enclosing metathesis, on the other hand, is one that maybe some in the audience have even run this transformation. This was first pioneered actually by Greg Fu when he was a postdoc in Scripps group. We'll talk about this more in a moment. But the basic idea here is that you have a diene, non-conjugated diene substrate that is capable of engaging in 2+2 and retro 2+2, that sequence at two different points on the substrate. As you see, I've drawn here all of these metathesis reactions are in equilibrium. So to drive them forward, you typically need some thermodynamic driving force. In the case of an RCM or a cross metathesis, that's most commonly going to be liberation of ethylene or another volatile alkene. And practically the way that can be done is that you run the reaction in an open vessel and let ethylene bubble out through your bubbler. You can do other tricks like run a reaction under static vacuum and so on and so forth. But typically, if you're doing an RCM, you don't want to do it in a sealed vessel where the reaction is just going to go forward and back. ROMP stands for, so RCM stands for enclosing metathesis, ROMP stands for ring opening metathesis polymerization. The key here is to employ some type of strained alkene. We used to say in the Grubbs group, no strain, no gain. And then the driving force here is strain release. There's another form of metathesis that it looks somewhat like a cross between cross metathesis, sorry, no pun intended, and ROMP, and that's called ADMET, acyclic diene metathesis transfer. That's where a non-conjugated diene is converted to a polymer under conditions in which constant purging of ethylene is operative. This is not as widely used as ROMP, as you can imagine. You need more specialized setup to make this go efficiently, but is still a transformation that you should be aware of. The other point I wanted to make, sorry, before moving on from ROMP, that's what I was trying to find in my lecture notes, is that this is important example of what we call a living polymerization. So when folks talk about what an impact that metathesis had in the polymer sector, this is really what they mean, is that this is a powerful version of a living polymerization. Living polymerization just refers to exactly what it sounds like. The polymer chain is actually alive. It contains an embedded catalyst, a reactive site at the terminus. So you can imagine what happens in solution. Let's say you're under romp conditions and you're romping some norbornadiene. You get to the end. What happens? Well, the catalyst is still intact, alive at the end of the polymer. So if you throw in another different type of monomer, it will polymerize that. And then you stop there. It will still be alive, and you throw in more monomer, and it will polymerize it. So that's a strategy by which you can make so-called block copolymers. One type of monomer in a block, different type of monomer in a block. Very powerful technology and materials. Okay, we talked about ADMET. Cross metathesis is analogous to a cross coupling. Two different olefins, and the key here is selectivity control. How do you get only the R1, R2 product and not the R1 homodimer or R2 homodimer? And there are some selectivity rules here that we'll discuss towards the end of class. But if you have unbiased olefins, then you can imagine that you'll get statistical distribution. So the name of the game in cross metathesis is how do you beat statistics? And this is actually not unlike, there's a connection here to some of the doubly decarboxylative cross-coupling chemistry of recently developed in the Barron group, where the name of the game is how to beat statistics. Right? Same concept here. And then you have E9 metathesis, powerful method to make dienes. I remember when I was learning about E9 metathesis, I was always confused at what the products should be from the starting materials. It's like not super obvious to me, or wasn't obvious to me. And the heuristic that I like to use is just thinking about breaking the alkene into two constituent alkylidine components and then just sticking them on to the two consecutive alkynyl carbon atoms. And this works. If you have a better way to do this, then you can tell me after class, and maybe I'll steal that way. But for me, this has always been a useful, quick and dirty way to just predict what the product outcomes are from the inputs. Okay, so we talked about ring strain considerations for romp, and the upshot here is that you need your monomer to have a reasonable amount of embedded ring strain for romp to be efficient. And so the things that you would normally see in the literature are norbornenes, cyclooctenes, or even better is cyclooctadienes. Those are more strained. You see the associated strain energies. Whereas if you were to propose romping something like cyclohexene, then someone would rightly point out that you have no thermodynamic driving force because that is relatively unstrained cyclic alkene monomer. So what will happen is open and close, and nothing productive will happen. You're a little bit better off when you use cyclopentene because there is enough ring strain that under some conditions you can efficiently romp that. This brings us to our chemist of the day, thinking about ring strain as it pertains to romp. Does anyone recognize this gentleman? Worksheet. No takers? Okay. This is Jan Shia from Stanford. Educated at Peking University, master for his master's degree, and then PhD with Grubbs and Julia Cornfield, postdoc with Brad Olson, and then also did a stint in industry at Dow before starting his independent career at Stanford. Has made a name for himself in the metathesis arena and also in development of some of these interesting ladder polymers. Some of that works in collaboration with our departmental alum, Noah Burns. So Jan's attention and his group turned to, if you were to just take this logic to the extremes, then and ask yourself, okay, if more strain is better, then what would be the most strained thing you could think about romping? Cyclopropene. Beautiful. And that would be reasonable to propose. It turns out and you have a ton of strain here, no problem there, 54 kcals per mole. At the time that some of this early metathesis work was being done, there weren't great ways to make cyclopropenes. Typically, they need to be dye substituted for stability. So they hadn't been actively studied. You could imagine a priori that these would just react like a shot, but actually it's more subtle and more interesting than that. So what Jan's group has found out is that rather than undergoing romp as one might expect, these instead react that's right. These react in a monoselective fashion and then stop. Why? What do you think, Shanghai? You look perplexed.
I'm not sure, actually.
Dylan, what are your thoughts?
So do you mind, I was in the paper, do you mind repeating the question?
No problem. You might expect, because of the ring strain, that these cyclopropenes would react like a shot and run. But in fact, depending on the substitution, it will react once and only once, and it will give you this new organometallic species. Why? What do you notice about?
There's something stabilizing about the ligands with the.
Okay, that's one interesting hypothesis, is that you could imagine that you might have some directing group stabilization. That is reasonable to propose, and I think that might be part of the story, but that's not maybe the main factor. What do you notice about that center?
Quad center.
Quad center, very crowded.
Right.
Comp is all about 2 + 2 retro 2 + 2. So this is very hindered for another alkene to approach, and the only alkene solution is more of this cyclopropene, which itself is quite hindered because it's doubly geminally quadruple. Its the allylic position with respect to both alkenyl carbon atoms is quaternary.
Are both olefins here coordinated to ruthenium? I can't quite make out.
I think it's phenol.
Oh, it's sorry. Oh, it's from the catalyst. I see.
Alex? So the cool thing here is that this is sterically hindered intermediate, and your coupling partner, even though it's very strained, is also sterically encumbered. So what happens is it won't react with another molecule of cyclopropene, but if you feed it in relatively unstrained cyclic alkene, this it can react with. So this is a strategy by which you can achieve alternating polymerization, something that's very challenging. So I like this example just because there are research frontiers that arise from what really are pretty simple questions. The simple question here is just, what if we take strain to its absolute theoretical limit and see what happens? You might think it's just going to explode the flask, but actually, even though it's more strained, the reactivity is more controlled in a way, and you learn something new. And then the insight from the Shia group was that even though it can't react with another molecule of cyclopropene, feed another different alkene, less sterically hindered, then it can. You can do that. Okay, let's now, so that's a modern example. Let's take a look at some of the organometallic history that's involved here. I'll try to go through this quickly since I know it's not everybody's cup of tea, but I think it's interesting and instructive to look at. So a series of early examples that certainly within the organic community were not fully appreciated are shown here. So one of the very first examples came from a team at DuPont. They were trying to carry out a Ziegler type polymerization with norbornene as the alkene. So remember we discussed how Ziegler Natta type polymerization is a means by which ethylene is converted to polyethylene, propylene is converted to polypropylene. Simple question, what happens if you put norbornene here? Well, you would imagine that this coordination polymerization would be the major product, but in fact, instead, the product is alkene containing. And that was a cue that something else was going on here. And in fact, this was the first way to make polynorbornene through ring opening. At the same time, or not the same time, but same decade, in a different sector, heterogeneous catalysis, this sort of gas refining type of transformation, it was observed that this particular heterogeneous catalytic mixture, cobalt oxide, molybdenum oxide, aluminum oxide, promote a transformation that at the time was referred to as olefin disproportionation. Where propylene, the C3 feedstock, was converted to corresponding C4 and C2 products, 2-butene and ethylene, respectively. And at higher temperature and pressure, this process can reach equilibrium. Natta, familiar name here from Ziegler-Natta polymerization, found that cyclopentene could undergo what we now think of as ROMP, at the time was referred to as homopolymerization. And he looked at two catalytic systems, one based on tungsten, one based on molybdenum, and found that they gave different products with respect to the alkene stereochemistry. And one of the key insights, and I think one of the unsung heroes in this area, came from a gentleman by the name of Calderon, who apparently was like an Israeli, in his former life before chemistry, was an Israeli paratrooper. He was the first to make the connection that this work going on in the gas refining, the petroleum refining sector, and this work in the polymerization sector might share common catalysts and common mechanisms. But he found that under quite similar conditions, the in situ generated catalyst could not only promote ring opening polymerization, but also could promote this olefin metathesis, olefin disproportionation. So we have the thermodynamic statistical mixture in the case of 2-pentene, 1 to 2 to 1 mixture of C4 to C5 to C6. So these observations were out there in the literature in the 60s, but the open question was mechanistically, how is this happening? And this took quite some time to resolve because it involved chemistry that was largely foreign to the world at that time. There's a nice CNU News piece from 2002. This is pre-Nobel Prize that I think frames the historical perspective in terms of mechanistic debate and some of the controversy that ensued here. So at the time, so now think back to the late 60s, early 70s. At the time, it was appreciated that the partners, the geminal partners of the alkene remained attached to one another. So rather than draw this as R1, R2, R3, R4, I just have this as deuterated and non-deuterated to try to make it as clear as possible. Geminal carbons remained attached to one another, and that rules out some mechanisms that you could potentially draw, but it's not conclusive about what mechanisms. So none of the corresponding crossover products are observed. You only get products that would correspond to double bond cleavage in that sort of manner. So what are the possibilities? Well, you see there are some pretty exotic mechanisms that were put forward. It's not necessarily important for you to jot all this down. You can find this in these notes, since it would be a lot to draw. Here's a familiar name here, Calderon. He proposed some hand wavy type of, or a cyclic type process where the metal is assisting in a reversible olefin 2+2, retro 2+2 process, but it's really unclear what exactly we mean by this and how the metal would promote this disfavored cycloaddition, orbitally disallowed cycloaddition. Landos and Pettit put forward something that, at least to my eye, looks even more exotic, where on the metal, these alkenes would spontaneously revert to their carbene states and then engage in recombination in a selective way. Again, I don't want to throw shade on our organometallic forebears, but it's just clear that there's when you look at these mechanisms, they look uncomfortable to the eye based on what we know now about elementary steps. Grubbs came along in 1972, and I just point out that he also got it wrong, but he got it wrong in a way that I think is at least the most logically consistent and instructive. So he got it wrong, but I think all the elementary steps here are things that look familiar. So it's essentially an oxidative cyclometallation, and then some type of mysterious metal migration followed by a retro oxidative cyclometallation, cycloreversion process. In 1971, Chauvin put forward the mechanism that we're now. So the difference here with the Grubbs pathways is that they're 5-membered intermediates. The Chauvin pathway is a 4-membered metallo 2+2, retro 2+2 sequence that now we're all very familiar with. And I think part of the controversy is that when Chauvin, it's unambiguous that Chauvin was the first to put forward this mechanism in the 1970s, but he published it in this small journal, which I think is a French-only journal. And so there's some debate about how much that publication actually influenced the zeitgeist at the time, or was just a publication that people found out about after the fact. But in any case, I won't get into that historical debate. So there's debate about how influential that was, and then also debate about who was the first to actually concretely show. It's one thing to have a proposal, it's another thing to actually have the mechanistic evidence to show that that proposal holds water. And so that's another point of the debate here, and I won't get into that part of organometallic history. I'll just direct you to these early reports by Casey and Tom Katz. The key insight from the Chauvin mechanism is that the propagating species is a metal carbene. And why did it take so long to arrive at that as a possible mechanism? Well, you have to remember that this is the late 1960s, early 1970s. When did the first reports of carbenes hit the literature? Fischer carbenes, let's say it's mid-1960s, Schrock carbenes, that's already in 1970. That's sort of contemporaneous. So this notion that metal doubly bonded species were important to consider in catalysis was something that was a little bit foreign, controversial at the time. And what made it even harder to reconcile was that the known metal carbenes, the Fischer carbenes that were known at that time, as well as the Schrock carbenes that were just being prepared here in the early 1970s, those did not do metathesis catalytically. So that's a problem. If your key intermediate, if you can make model versions of your key intermediate and they're not metathesis active, that's a problem. So that changed then in the late 1970s, early 1980s. So after Schrock's first report of the Schrock type alkylidine, the tantalum alkylidine in 1974, which was metathesis inactive, he eventually found a variant of this with tuned electronic properties that was metathesis active, albeit a poor catalyst. And then with that insight, was able to pivot to the metals that we most commonly today affiliate with Schrock, molybdenum and tungsten. And here are some of the more modern looking catalysts that can perform metathesis with tens of thousands of tungsten. So this was all happening in the 80s. The Grubbs catalyst chronology begins almost a decade later. And the insight here was to look in somewhat of an unexpected part of the periodic table, look towards ruthenium, so a far later transition metal than the ones that were being actively studied at the time, and really right at the border of what would even be possible to promote catalytic metathesis versus just giving CC reductive elimination from the corresponding metallocyclic butanes. Why did the Grubbs group get interested in ruthenium? That is an interesting and somewhat bizarre story. It had to do with an idea at that time in the Grubbs groups, and this is late 1980s. They wanted to make these ionophore polymers by romping a monomer that looked like this, an oxanorbornene. They thought after romping this, it would make some helical structure with the oxygen atoms pointed in the middle, and this could form ion conducting channels. Very wild idea for the 1980s. And it turns out most of the catalysts at that time, the moly and tungsten catalysts, they did not romp norbornadiene. And they made this hypothesis that the reason was because oxygen, Lewis basic intolerance with these early transcripts. They dug up this paper that showed metathesis reactivity of ruthenium chloride hydrate in water. Ill-defined catalyst, but the key point was if it can tolerate water, it can probably tolerate a lot of heteroatoms. And so based on this report, they revisited this. They found that it did indeed perform romp of oxanorbornadiene, and they got curious. Well, there must be a ruthenium carbene here that's generated in situ. So can we prepare a well-defined ruthenium carbene and use that as a starting point? Would that be an active metathesis catalyst? And indeed, in the early 1990s, they were able to do exactly that. This is the first, it doesn't even get a generation name. It's like a G0 catalyst. This was developed by first made by Sonbin Win, who some of you will know is now a faculty member at Northwestern University working at the organic chemistry materials interface. And does anyone want to hazard a guess on how this is made? Where do carbines come from?
Can you make the corresponding diazo?
You're getting ahead of me, Shenghua. Actually, that's a familiar friend. This comes from the corresponding cyclopropene plus ruthenium chloride plus ligand. There's some interesting connection here that this cyclopropene chemistry was on Bob's mind based on his PhD work with Breslin. Shenghua provided the synthesis that is more modular. So if you don't want this dienyl or this vinyl carbene moiety, then you want to do this in a more modular way. You can do that from the corresponding diazo species. Similar logic, diazo plus ruthenium plus ligand. That's how you make all of these catalysts for the most part. So now we get into the generation counting. So if that's G0, then this is G1. I don't think people even call that. So this is G1. Hoveda came along in the mid-1990s and made the contribution that if you add this chelating benzylidine group, now a ether or other heteroatom substituent can occupy the position that's normally occupied by phosphine. And that is important, particularly with the NHC containing catalysts, because then it will be phosphine free, and phosphines turn out to actually be involved in some catalyst decomposition. So we talked about the importance of N-heterocyclic carbene ligands. And it turns out that metathesis catalyst development, ruthenium metathesis catalyst development, was really one of the earliest, most significant examples of carbenes having an impact in catalytic reactivity as ligands. They were still quite new at the time in the 1990s, but what they did in terms of improving catalyst performance in metathesis is what ultimately sparked everybody's imagination. So the first to consider NHCs ligated to ruthenium benzylidines were several groups working at the same time. Firstner, Wolfgang Hermann, Steve Nolan, and Grubbs group. They all looked at the unsaturated backbone version. And then the Grubbs group found that actually this modest tweak of going to the saturated backbone is important. This led to what we now call the G2 catalyst. And what does the carbene do compared to the phosphine? Well, as we'll see in the mechanism, it turns out the first step of catalyst initiation from these pre-catalysts is loss of the, in this case, the tricyclohexylphosphine ligand to get to a 14 electron complex. At that point, the catalyst has two choices. You can either find the phosphine back or find an olefin. When you have an NHC, it finds the olefin 1,000 or 10,000 times more frequently than it finds than it does as compared to when you have only phosphine ligands on. So it changes that the chemoselectivity that is so important for catalytic reactivity. The initiation of these catalysts is important. And the standard ones, G1 and G2, that we use as organic chemists are not very fast initiating. So for materials applications, people normally use this bispyridyl ligated catalyst, which is called G3, the third generation catalyst. We've used it in our lab actually for synthesis, but in general, it's used mostly for polymer chemistry. And if you're really following this literature closely, you'll know that in the past decade, there have been really significant advances in kinetically Z and E selective catalysts. So I've drawn here the kinetically Z-selective catalyst. It's such a bizarre looking organometallic complex. And there's a whole, I think, a whole lecture just on this Z-selective catalyst. But just so you know that if you want to do a cross metathesis with controlled E or Z stereochemistry, there's catalysts out there to do that for you. Okay, let's take a look at an overview that I think provides some general orientation on how to think about the different catalysts that you'll encounter in the literature and their chemoselectivity trends here. And I've largely copied this and added a few details from this Accounts of Chemical Research paper from 2001, if you want to read more about this. But the key point is that if you consider, bless you, metathesis active metals from titanium to tungsten to molybdenum to ruthenium, each of these have different intrinsic chemoselectivities for different functional groups that you encounter in synthesis. So the reason why people tend to use ruthenium olefin metathesis catalysts in synthesis is not because they're the most reactive. In fact, molybdenum and tungsten catalysts are almost always more reactive in terms of turnover frequency. It's the chemoselectivity. Ruthenium olefin metathesis catalysts will react with olefins in preference to almost any other functional group. I should add as a caveat that since this 2001 report, there have been developments of tuning tungsten molybdenum-based catalysts through introducing new ligands like NHCs, et cetera, that do improve chemoselectivity. But in general, this trend still holds. And this reactivity trend, I think, you can view as being a consequence of the electronegativities of the corresponding metals involved, reflecting themes that we've seen again and again in the class of early transition metals typically reacting quite preferentially with heteroatom-based functional groups due to the way that carbon metal bond is polarized. So the general trend is as you move to the right of the periodic table, the functional group compatibility improves, but there's sort of a theoretical limit right as you get to rhodium, because once you hit rhodium, you can't go any further because you start getting competitive CC reductive elimination for the metallocyclobutane. Okay, let's consider we have a couple problems of the day, but they're pretty short. So let's consider the first one. I guess let's do the first two here. So 1 and 2, we'll just do them together back to back. So take a minute to look at each of them and I'll share the screen. Worksheet handy. So the first one asks you to rank the order of reactivity under pseudo first order conditions. So this is not catalysis. This is just focusing on essentially group transfer, 2 + 2, and then retro 2 + 2. So don't be confused into thinking that we're talking about a catalytic turnover process here. Olefins A through E with different substitution patterns. So this is challenging you to think about how substitution pattern and stereokindrence will affect reactivity. Question 2 asks you to consider, again, not catalysis, this is a stoichiometric example, treating this alkenyl ketone with an equivalent of the Schrock metathesis catalyst or complex in this case, and predicting the product. So let's take a look at these two. All right, Christine, what do we think here? Get me started. What do you think is the most reactive?
A would be
Okay, okay. Why?
the least substituted.
Okay, very good. What do you think next, Pranali?
Then I probably go.
D, okay. Why do you say D?
Well, because, or actually, no, sorry. I think I'd go B.
You would go, sorry, what, B, okay. But why, originally you like D?
Yeah, because I guess, because B is less substituted, but D looks like the least compared.
Okay, follow your instinct. Follow your instincts. D is good. This is hard because I think you're comparing things where there's not necessarily one-to-one comparison. So that's why we have this discussion. So I think the way you're thinking about it is right, but I like that intuitively you looked at D and you're like, oh, wow, that looks like it could be the next one. Okay, and then what about after that? Give me one more. If you like D, then E is not so bad looking, is it?
Yeah,
Okay,
C.
all right. And the key trend here is that Z is more reactive than E in terms of double bond geometry.
Right.
That was my last chance to get through full lecture without making that mistake, but alas, it was not to be. Okay. So the key trend here is that Z is more reactive than E, and that single substitution is more reactive than 1,2 di substitution. Okay, give me something next there. Cindy, what do you think? What do we have left? Okay, we got C and D. Both look unattractive in their own ways here. They got 50% chance. C, okay. And that would put E as the last one. Very good. And that is indeed the correct order that you can get out of this paper. C and B, they're tricky to compare. Remember, really try to put yourself in the, imagine you're the catalyst and you're approaching these alkenes. And the key determinant is this metallo 2+2 transition state. And between C and B, C's steric bulk is a little bit removed. It's not directly on the alkene that's engaging in bond formation, whereas B, it's 1,1 di substitution. So it's like however you orient, however you engage, there's going to be some bad steric clashing, right? So that's sort of the difference between those two. So another key trend here to draw your attention to is that 1,2 is more reactive than 1,1 di substitution. And there's actually, as it turns out, A, D, and E all react within like an order of magnitude of each other, a factor of 2 or 3, I think. And then C is substantially slower, like I think 2 orders of magnitude slower, something like that. And then B just essentially doesn't react under the reaction conditions in which this experiment was done. So I draw your attention to this reference if you want to read more, but I will add as the caveat that this paper, because of its timing, late 1998, the mechanistic discussion is a little bit wonky. So for the mechanism, you need to look at a later paper, which is the one down here, this 2001 paper. So you can look at the rate data there. It's good data to look at, helpful, but then don't get confused by the mechanism. Okay, problem of the day number 2. Let's work through this one. Can you get me started, Annabelle? D6. Oh, you said? Oh, D0? Sorry, I just didn't hear you. Molybdenum 6, okay, plus 6. Okay. And then D0.
B14 since it's a linear nitrodo.
Oh, yeah, we have this linear amido that implies donation of the lone pair. So it's an LX2. Okay. 14. Beautiful. Okay. And Jalen, what about mechanism here?
I think it's gonna go with the alkene first.
Why?
It's less hindered and
Well, here we can just consult our handy dandy chart and see that alkene from molybdenum and almost the same catalyst is more reactive than ketone, right? So that's going to dictate initial selectivity. Now what?
it's the ketone
Then it hits the ketone.
and cyclized.
To make a 7-membered ring. Now you all get to judge my inability to draw 7-membered rings here. Isn't too bad. And the byproduct?
Metal oxide.
Metal oxo. So do you think this could be turned over catalytically or not? No, that's the dead end. So this is a very important early example of carbonyl olefin metathesis, a transformation that's continued to captivate the synthetic community for 20 years. Beautiful, powerful in a forward sense, but can't be turned over catalytically because of this molybdenum oxo generation. But it's a beautiful example, an early example of ring closing metathesis, also of how you can choreograph through chemoselectivity of the catalyst, which functional group is engaged first. Wonderful. Any questions on that? Okay, we're quickly running out of time, but give me just a few minutes since this is my last time to present. What I'm going to share here can all be found in this 2003 paper, which defines the cross metathesis selectivity rules. Interesting fun fact here is that the first author of this study is our very own Arnab Chatterjee from Caliber, who you might know from being the architect of this famous reframe drug repurposing library. He was a PhD student before his time as a medicinal chemist, a PhD student with Grubbs, and published this seminal paper, which I think is still one of the Grubbs's 10 most cited papers, so it's very useful. There's a handout that you'll receive that has more details about this. The key concept in this paper is that it defines different types of alkenes based on their substitution pattern, based on their polarization. And it notes that the type is catalyst dependent. So a type 1, let me say that again, a type 3 olefin with the molybdenum catalyst is not necessarily a type 3 olefin with a ruthenium catalyst. So that's an important thing to keep in mind. This cross metathesis selectivity rules paper allows for kinetic selectivity beyond getting statistical distribution. So if you're happy with statistical distribution, then that's fine. And you can even, if you're at the mercy of statistical distribution, you can still help yourself by like loading up on whatever the cheapest coupling partner is to try to drive your yield up. But let's consider the olefin, just for the purposes of illustration, let's consider with the G2 standard catalyst. Then the 4 olefin types break down as follows. monosubstituted alkyl alkenes fall into the type 1. Type 1 olefins are those that undergo rapid homodimerization. So you put them in and they're giving you, they're spitting out ethylene and the corresponding homodimerized product. Type 2 olefins undergo slow homodimerization. In the case of the G2 catalyst, those are things like acrylates. And so homodimers do form, but not much. Type 3 olefins, in this case, are things like 1,2 disubstitute alkenes. Those don't undergo homodimerization. And then type 4 are olefins that are essentially inert to metathesis. In the case of the G2 catalyst, that would include tetrasubstitute olefins. So they're just going to be spectators to the show. And so now here's the upshot of the paper is that when you try to cross a type 1 and type 1, you're going to get a statistical distribution. There's not much you can do about that. When you try to cross type 2 or 3 or 2 and type 2 and this looks like a typo. Maybe it's type 2, type 2, type 2, type 3, then you get non-selective. But you can get selective cross metathesis when you pair a type 1 olefin with a type 2 or type 3 olefin. So what does that mean in practice? If you want to cross like an ethyl acrylate with 1 dodecene, then you can beat statistics because the elementary steps are naturally choreographed in your favor, meaning that the 1 dodecene will engage the catalyst first, it will give a propagating alkylidine, and the acrylate will engage next, and this choreography is essentially on your side. So that's confusing without actually looking at the mechanism. So here's the mechanism. Again, this seminal paper from 2001, this is the lead on this is Melanie Sanford, who really made her name as a young scientist, mapping out the mechanistic details of this transformation, which at the time were ambiguous. So the key point is that from the 16-electron ruthenium benzylidine starting materials, the first step is loss of a ligand to get to the active propagating 14-electron species. Then you have a 2+2, metallo 2+2 step, retro 2+2 to give a new, in this case, a methylidine. Now, methylidines are typically kind of unstable, so they'll decompose. That's a way in which catalytic reactivity is lost here. And then you can coordinate your second molecule of alkene. So what do we mean when we say things don't undergo homodimerization? Well, let's consider the case where we're like bulking up, hypothetically, we're bulking up this group. Then you start to make species that are, oops, I should make this. R3, you start to make I should draw this with the opposite orientation for point of so you start to make very highly substituted alkylidines that then are not able to engage another molecule of that very hindered alkene to promote what would need to happen for the homodimerization. So that's what I mean when I say that things are choreographed to happen in a particular sequence of events based on steric and electronic properties. Are there any questions on that? Okay, we can close by quickly considering the last problem area, which hopefully will be appealing to in photosynthesis. There's an example out of photosynthesis project from the lab of John Porco. Starting material here is pretty complex. Starting materials. And you see there's the key difference is that A I'll just do it on key difference between these two is that A contains this terminal olefin, and whereas in B it is internal olefin that's tethered to yet another terminal olefin. So there's a substantial difference in yield here, which if you're put yourself in the shoes of the students, this is not going to be acceptable to at this stage of the project get 15% yield. You really want the 70%, even if it means additional steps up front. So what would be the potential difference here? I'll just take a volunteer.
Maybe that terminal olefin does like a sort of dummy metathesis at the start and B, so you make this hexene.
I love that. You call it dummy metathesis, but the terminology that folks in the literature use is relay metathesis. This was pioneered by Tom Hoy, University of Minnesota. And I think you hit the nail on the head. You said this is going to spit out, what is it? 1, 2, 3, 4, 5 cyclopentene. Thank you, Alex. And that's going to put your ruthenium right where you want it for metathesis. Now you can cross to this diene here and off you go. What happens in the other case, why this one doesn't work so well is that in theory, if you engaged that epoxide alkene, you would get to the same intermediate. And that would be good, but that's not what happens, unfortunately. It happens some of the time, enough of the time to get modest yield. But what happens most of the time, sorry, I'll try to spread these out so it's less confusing. Is that instead it crosses onto this diene, where it reacts with this diene. And this is inactive. So relay metathesis is a strategy by which you build in a little additional complexity at the start, but it allows you to, it's essentially a substrate directivity strategy to direct the catalyst to exactly where you want it with more functionalized substrates where chemoselectivity is a problem. It doesn't have to be this particular design. People will also use allylic alcohols or their derivatives that benefit from the allylic chalcogen effect, and then you kick out something like a dihydrofuran, and that can even be easier to access synthetically. So those are the types of strategies people use in this relay test. Do you have a question?
Just an allylic strain issue, or like the hindrance of trying to activate that olefin closer to the epoxide.
Right. So at the allylic position, it's more hindered.
Yeah, okay.
That's one factor. And then the other factor is that I think that the diene in general is more electron rich. So there's probably some pre-association that happens from the alkene being able to engage in like 8-4 coordination to the diene that pushes it that way. Good. Any questions? Okay, thanks to everybody for bearing with me a few extra minutes, and see you Thursday.